I wanted to show just a little bit of some applications of thermochronology and talk a little bit about the idea of calculating exhumation rates. So that's our kind of goal here. We want to talk about rock exhumation and how do we get a rate of exhumation, and then take our geological excursion to the Himalaya of central Nepal. And I can't talk that up and not get there, so we'll make sure that happens one way or another. So the thermochronometer ages by themselves are useful, but I think most people who go out and use thermochronology don't care that much about the age itself. They care more about what that age means and what that age tells you in terms of a process in the earth, what it tells you about tectonic processes, what it tells you about erosional processes over long time scales. So we know with this effective closure temperature idea that we can take an age and we can relate that to some temperature in the earth. So that's useful. The next step then is to take that temperature and say, okay, what depth does this temperature correspond to in the earth? Because if we want to know what the rate of exhumation is, we know the rock is at the surface. How deep do we have to go to get down to whatever temperature, 110 degrees or 250 degrees or whatever? And if we know what that depth is, then we have the possibility to calculate the rate at which the rock went from that depth to the surface where we collected it and measured. And so we can do that, by calculating what the paleo temperature was, because of course, remember, this temperature doesn't, temperature 50 million years ago doesn't necessarily need to be the same temperature at that same depth today. Or we can take advantage of what I've called some quote-unquote tricks, which is just sort of recognizing something about what the ages record and taking advantage of that. And this is just one such trick. So this is what's called the age elevation approach. If you've learned anything about thermochronology in mountainous areas, this may have been mentioned. This is kind of what was done. It's still done to some degree now. But this was really kind of what was done back in the 70s and 80s when modeling thermochronometer ages was a little bit more difficult than it is today. The concept is essentially this. If we look at a high temperature thermochronometer, something maybe that's sensitive to 550 degrees or something like that, its closure temperature isotherm will more or less be horizontal. And if we assume that we just have very slow rock exhumation and there's no complications of tectonics or anything like that, we can look at a picture like this. We have these red dots at the surface, and this might be where we walk along and collect our mineral samples. Now, when we look at the ages of these samples, more than likely we're going to observe something like this, and that is that the ages are youngest at low elevations and oldest at high elevations. So I mentioned this already. Why is that? Well, we can see the picture here. So if these are our rock samples sometime in the past, what you see is that the particles that are going to end up at the surface, these rock parcels or whatever, that end up at the surface, start out at some depth here where this sample is just passing through the closure temperature at this time. And as it moves up toward the surface, the particles move to shallower depths. So now these two have already passed through. This one's passed through the closure temperature, but these haven't. So the clock has started counting for these samples here. But these samples down below the closure temperatures haven't started recording the daughter product, or the clock is not recording their exhumation history yet. As you continue, now we have all of these rock samples below the closure temperature, but the ages here, of course, are going to be a bit older because they passed through the closure temperature earlier for these samples that end up at the surface. And so what you see here is essentially this kind of trend where you have an increase in sample age with elevation. What's interesting about this, and maybe not something you appreciate right away, is that if you fit a line through these samples, this slope of this line is actually the rate of exhumation. Because the only thing that these samples, the only thing their age depends upon is the difference in elevation between where the samples were collected. If they're all moving at the same rate up toward the surface, you can just put a regression line through this data, and that will give you the average exhumation rate for those rock samples. So that's kind of nice because you don't even need to do anything with any kind of thermal model. You don't have to assume, a constant geotherm or anything like that. You can just basically take these distribution of ages, fit your regression line through it, and boom, you've got your exhumation rate. That actually works surprisingly well in tectonically inactive areas because you don't have to worry about faults that might be moving rocks horizontally and transporting heat horizontally, and for high temperature systems where you can assume this isotherm is horizontal and not bent by the topography. So this is kind of neat because, well, what's different? Nothing here. So yeah, here are some scenarios where this kind of idea works. One is where the closure temperature isotherm is horizontal, which means in many cases, places where you're dealing with relatively high temperatures for the temperature sensitivity, or very little topography. Now, if there's very little topography, this vertical difference in sample elevation is going to be small, and it might be so small you can't tell a difference in the ages. But if you take, for instance, this scenario here, these three ages, you calculate their age versus the sample elevation, and you put this slope of this line through here, that gives you the exhumation rate. And you can even also calculate the depth to the closure temperature this way if you want to. The other situation in which this works is if you have a perfectly vertical set of samples and vertical rock exhumation. So if you have a cliff face or something like that, there's some people that have done work in some of the national parks in the western US, for instance, where you have these big glacial valleys and like 1.5 kilometers of just wall. If you're, skilled enough at climbing to collect the samples, you have a perfect sampling scenario because you can just go right down that wall. You don't have to worry about anything about whether that closure temperature isotherm is bent or straight, because there, if rock is being transported vertically up toward the surface, the difference in elevation is just going to give you different ages, and again, you can get the exhumation rate straight away from that. So those are good pictures. Now, as you can imagine, finding these kind of scenarios in nature, you don't encounter too many places where you have, 1 kilometer or 2 of vertical exposure of rocks you're trying to date. If you're, working on a project where a borehole is drilled, that might be one possibility, but that's not cheap, and you may have to battle to get the rocks out of the borehole as well. And the other thing is, here it's a bit challenging to know whether the closure temperature isotherm would be horizontal. So more often than not, this is what we have, and that is for low temperature thermochronometers in particular, we have some topography and some closure temperature isotherm that is also bent to look like that topography. Here, the slope of this line is not going to give you the exhumation rate. And, well, here's kind of an example why. The problem essentially is shown simply here in some kind of case where we have, this is normal faulting, you don't see the fault surface here, but these rocks are moving up toward the surface like this. You can see the closure temperature isotherm here is bent and following the topography, and as a result, these samples pass through that closure temperature at different depths. Because they pass through this closure temperature at different depths, the slope of this line does not give you the exhumation rate. So in order to be able to take advantage of this with low temperature thermochronology, you really have to take samples that are as close to vertical as possible in how they're sampled, or recognize that you can't do this simple slope regression thing without getting some kind of exhumation rate that's going to be overestimated or higher than it should be. So, I call this the trouble with low-temperature thermochronology. Well, it's not really the trouble with the method, it's more the trouble with trying to do this age elevation trick with low-temperature thermochronometer data. So, we know that we're fairly sensitive to topography with these low-temperature systems because the topography will cause the isotherms to be bent. But we haven't talked about anything about the wavelength or the sort of the scale of the topography and how it affects things. And so that's what I want to look at here next. These again are kind of cartoon scenarios, but give you some idea of what happens for different wavelengths of topography. So if we have short wavelength topography, so maybe this means that river valleys are quite closely spaced together. If the variation in elevation is over a very short horizontal distance, the closure temperature isotherm doesn't adjust to that short wavelength change in topography, but rather ends up being something that's actually closer to horizontal. Now, there's not necessarily a kind of clear reference point for what this horizontal wavelength should be in order to end up with horizontal isotherms. But the point is that for very short changes in elevation, short wavelength changes in elevation of the surface, you can end up with horizontal isotherms. Here, if you collected rock samples along one of these little ridges or along one of the valley walls, you could do the regression line with the age elevation relationship and should get the exhumation rate. At the other end of the spectrum, very long wavelength topography will affect temperatures quite deep into the earth. So if you look like from the Tibetan Plateau down across the Himalaya toward the Indian foreland, there is a very long wavelength bending of isotherms beneath that whole region. And so, at the opposite end of things, here the topography and the closure temperature isotherm might actually be exactly the same shape. If you do this regression line thing on a closure temperature isotherm that's the same shape as the topography, you'll get an infinite slope. It will be a vertical line because all of the ages should be the same. And if all the ages are the same on a plot like this, then you're going to get a vertical line, infinite slope. Okay, we know the exhumation rate's not infinite. It's just this is the reality of the crustal temperatures. And people have played with this. So here's a figure out of a paper from Kurt Stuve in 1994, where he used some kind of simple numerical model just to look at different rates of exhumation and different wavelengths of topography to kind of see how much does this affect. I think in this case it's 100 degrees C isotherm, so kind of around the fission-track in apatite closure temperature. How much does this topography affect these isotherms for different rates of uplift and exhumation? And you can see for very slow uplift, there's a little bit of bending of the isotherms, and as you go to higher rates, it gets bent more and more. But what this tells us is in mountainous areas where erosion rates are high, those are normally places where we want to go and use thermochronology. They're also the places that are probably worst in terms of this bending of the isotherms issue. So regression lines for sample age versus elevation just won't work. So there's some alternatives. We could say, well, who cares about doing that age elevation thing? We can just calculate what the temperature is at depth, and we'll start the simplest case, which is just to assume the geothermal gradient is constant. Now, I get like nasty look from Ilmo if I say that that's what happens in nature, but that's one possibility. And I don't advise this, but it's possible. So you say, okay, let's Well, let's put you guys to work for just a second here. Let's assume we have some apatite uranium, thorium, helium age. Again, we don't know what that means yet, but we know its age is 4.2 million years, and we know its closure temperature is about 75 degrees C. The question for you is, what's the average rate of exhumation if we assume a constant geothermal gradient? I have not given you that gradient because I'd like you to take a guess. Use some value that you think is a reasonable number for a geothermal gradient, and just take a moment to calculate what the exhumation rate would be. So, it's not a good idea to assume a constant geothermal gradient. You can see that just in the kind of picture here, and just kind of highlights that there's two problems. One is that geothermal gradient is usually higher at the surface than it is at depth. We can't see that necessarily in this picture, but we might see that this afternoon. But also, we see that these closures, these shallow isotherms are affected by the topography. So the geothermal gradient beneath a mountain peak will generally be lower than it is beneath the adjacent valley. So, and you can see that here, that the distance between 100 degrees C and the surface is higher here than it is over here. Because of that, the geothermal gradient is varying in space. And so obviously you can't assume a constant gradient even across samples that were collected going up one of these. If we went from the river valley to the peak here, you can't use the same geothermal gradient for all those samples to get exhumation rates. It wouldn't make any sense. So we can do some thermal modeling, and there's varying degrees of complexity that can be done here. These are just some kind of examples showing temperatures here for some model that starts with an initial temperature field like this and has an uplift rate of erosion rate of 1 millimeter per year, 1 kilometer per million years. And you can see temperatures are increasing as a result of that rock being eroded and moved toward the surface. This is a 1D picture. Here's a 3D example of a little bit more complex thermal model where there's faults that are active and things like that. So I don't want to miss out on the geological excursion. So we'll take a quick look now at some work I did a while ago now, but in a kind of interesting area, the Himalaya of central Nepal, and where we can look a little bit about the thermochronometer ages and some modeling and kind of how these different pieces fit together in one case study. So the study area is here, and this picture probably doesn't really show so much, but we're in the Himalaya of central Nepal, and you can see there's high peaks here that are all kind of snow-capped. Some of them, I guess, I can't see where Dhaulagiri is, but it's there's one peak at least within this picture that's above 8 kilometers elevation, so quite high elevation. But you can also see these very big river valleys here. So there's one running up this way, the Marsyandi River Valley, that we're going to look at. And so this is the Marsyandi region, just zoomed in on topography a little bit. So this is the Marsyandi River. It's quite big river valley. It doesn't make it all the way up to the Tibetan Plateau like some of the neighboring rivers, but it's a big river valley. And kind of also a popular trekking area for people who want to hike in the Annapurna region of central Nepal. We're going to start over here, though, in the Modi River Valley, which is just a little bit to the west, because I was there and did some field work a while ago, so there's some pictures we can look at to see what things look like. So this is the kind of lower elevation regions here, so down to kind of in the areas where you can see it's sort of clearly forested, kind of darker green color. In what you can call the Lesser Himalaya So relatively low elevations looking up toward the higher peaks of the high or greater Himalaya. And you can see down here there's a lot of vegetation. Can't see it so well in this picture, but maybe in the next one you can see there's also a lot of like agricultural use of the land, and plenty of moisture for plants to live and things like that. Here you can see kind of the terraces for where people are growing vegetables. And this is a kind of pretty typical picture. It's clearly mountainous. There's obviously some kind of topography here, but if you look at the slopes of these hill slopes, they're somewhat gentle, not super steep, and obviously stable enough that you can use them for farming. This is just another picture as we kind of go up to a little bit higher elevation of rhododendron forest. I don't know if any of you know what rhododendron flowers are. Maybe you've seen them. I don't know what they're called in Finnish. Maybe Ilmo knows. Okay. Yeah. Well, we have a rhododendron in the backyard of the place where we're staying right now, and it's I guess maybe it's about this tall. That's pretty typical. They normally like kind of a shrub or kind of a bush, but for some reason I don't know what it is. They just love this kind of intermediate elevations in the Himalaya, because some of them get to be like 10-15 meters tall, and it's really quite spectacular. Like when they're in bloom on the you can see these are pretty tall. This is the footpath here, so these are probably at least 10 meter high rhododendron, yeah, they're really just quite beautiful. So anyway, this is going up to higher elevation. This is looking across to the Dhaulagiri range. So Dhaulagiri 1 is this peak here. It's not quite 8.1 kilometers above sea level, so it's quite high. In the river valley down here, the Kaligandaki River is at about 2.5 kilometers elevation. So there is a massive amount of topographic relief between this peak and the river valley over a relatively short horizontal distance. So to get up to these high peaks, we're looking off to the northeast in this picture, and you can see here a landslide scar. There's a landslide scar here, a landslide scar here, a couple landslides there, one there, one there. As you get up to the higher elevations, you start to see landslide scars all over because the landscape is getting steeper. And so that's kind of one of the indications you see in the geomorphology that you're getting into the higher part of the Himalaya. Of course, here getting closer to the high peaks, you can see, still a decent amount of vegetation on the hill slopes, and then behind there at the higher elevations, there's essentially nothing but bare rock exposed. Again, similar kind of picture. This is about as high as we went when I was there, and it was only, I don't know, a little over 3 kilometers elevation. We didn't go, we weren't going to kind of go climb the peaks or anything like that. But you can see already that the landscape is getting significantly steeper here at these elevations. And this is a river valley here, and these boulders that are in the river, some of them are quite large. Like this is probably, I guess, 8 to 10 meters high boulder sitting in the river. And from what I've heard from people, these kind of things are gone from year to year. So at sort of come monsoon season, there's a lot more water in the rivers, and even very, very large sediment will move. My suspicion is that this stuff, it kind of rolls over once or twice and breaks into smaller pieces and then gets whisked away. But yeah, that's just kind of the photo tour. Here's the area of the Marsyandi River that where I was fortunate to work when I was a student. And we basically wanted to test 2 different hypotheses for what had happened with the tectonics there. So this is showing the main thrust fault that sits underneath the Himalaya, the main Himalayan thrust. this would be the Indian craton that's being subducted to the north, and then these are the thrust faults in the Himalaya that are actively thrusting material up to the south. The question was whether this thrust fault here, the main central thrust, which was a major structure active in the early Miocene, had been reactivated in the last few million years. There's some geological evidence that would suggest it's been active recently. And we had samples that were collected in the hanging wall of that fault, and so we thought maybe we could distinguish between the cooling history of the rocks that would be transported like this versus rocks that would be transported along a path that's parallel to this main Himalayan thrust. And the difference in those two cooling histories would allow us to tell which one of these tectonic scenarios was more likely. So there was a bunch of fission-track, apatite fission-track data, and we'll learn about that stuff on Wednesday. But it was collected in these kind of vertical transect type fashion. And here's the main river valley. You can see the different transects going up in various orientations from the river valley to try to understand the rates of rock exhumation. Here, the different ER, those are the erosion rates. And so you can see that, this transect here suggests an erosion rate of 1.6 millimeters a year. Just across the river valley over here, we've got an erosion rate of 12 millimeters a year. Again, calculated from just doing this slope of the sample relationship with elevation and age. And so there's a bit of variation in the ages there. But that's the data. And that picture I showed before of the thermal model was an example of the thermal modeling that we had done with this 3D thermal modeling software, where we could put in the different faults, have them slip at different rates, and then use that cooling history that we would predict for faults slipping in these orientations to predict cooling ages and then compare it to what we observe. So I won't talk about the details so much. If you're curious, I'd be happy to talk about that when we take a break, but that's the kind of general picture. And to kind of jump to what we found out, essentially we found out that we're not sensitive to these different tectonic scenarios. So we had measured how well the predictions from the model fit what we observed with a fairly standard statistical comparison to chi-squared statistic. All it does is just difference the observed and predicted age and divide by the uncertainty. It gives you kind of a sense of whether you're within the measurement uncertainty or not. And here, if it's below the dashed line, we use that as representing a good fit between the model and the predictions. So what we see here is a case where all the thrusting is on the one main Himalayan thrust versus another case where it's split equally between two structures. And essentially we get an equally good fit in both scenarios. So we can't tell the difference between thrusting on one fault versus having both faults active. There's no question that that all the activity is definitely not going to be on this main central thrust, because we have evidence of very young deformation at the very southern edge of the Himalaya. So we can't say that maybe more than about half would go onto this other fault. But what we do see is that we have a certain range of erosion rates that are consistent with the uplift for these two models, and we see that basically that same range of erosion rate shows up no matter how we distribute slip on the different faults. So the thing we set out to test we couldn't do, and maybe this is just a useful thing to hear as young scientists, that sometimes you come up with some idea of what you want to do. You think you've got a very good team you're working with, and everyone seems to think we're going to be able to test this hypothesis with these great methods, and then the reality is that here, because of the sample uncertainties, we simply couldn't tell the difference between these different scenarios. The ages were very young and they had fairly large uncertainties, and so if we consider the uncertainties, basically see that both tectonic models would fit equally well to the data. So I think I'm just going to kind of maybe skip over this. These are just the variations in erosion rates that you can calculate for the different transects, and you can see they vary a little bit, the rates of erosion. But here, for instance, I will maybe just say that this is the transect with the slope of the age elevation relationship suggested in an exhumation rate of 12.2 millimeters per year. We get a rate that's more like 3 millimeters a year with the numerical model, because remember that rate that was calculated from the slope of the regression line is not accounting for the fact that the isotherms are bent beneath the topography, whereas this numerical model would simulate that. This rate is just calculated based on the rock cooling through the closure temperature to the surface. And if that doesn't make total sense, don't worry about it. So, we basically found out we couldn't tell between the two tectonic models. We see erosion rates of something like 2 to 5 millimeters a year in the central Himalaya. Those are pretty high rates of erosion. If you take those out to kilometers per million years, that's 2 to 5 kilometers per million years of rock erosion. So that's quite significant. And we saw that if you use that slope of the age elevation relationship, you see quite a big difference between the rates of exhumation from the numerical models and from that slope regression method. So don't do that. It's not a good idea. And the last thing I want to say here just has to do with thermochronology in general, and that is to say that we've seen one example from a modern tectonic setting. Ilmo's going to talk a little bit about rock exhumation in ancient settings like we have here in Fennoscandia. But thermochronology is really a global tool. This is a figure out of a recent compilation of thermochronometer ages from across the globe. And you can see that there are some places where thermochronology has not been used, or at least not published. But in many places, maybe the data density is highest in these mountainous areas like the Himalaya, the Andes, some of the mountain ranges in Western North America or Southern Alps of New Zealand. But there's a lot of places in Australia that aren't necessarily that mountainous where thermochronology has been applied. Northern Europe, it's been applied a fair amount. Look at, most of Europe has been dated in one way or another with thermochronology, and all of these studies are after slightly different things. Here, the point of doing the global compilation was to look at the differences in rates of erosion 4 to 6 million years ago compared to the last 2 million years. And what they ended up finding is that the rates of erosion, when you compare erosion rates 0 to 2 million years ago versus 4 to 6, the erosion rates in the last 2 million years have been something like 3 to 4 times faster than the average in a lot of places. And in this case, the authors linked that to the onset of glaciation in the northern hemisphere and the sort of the destabilization of climate. So essentially, when glaciers became active and filled many of these valleys, the rates of erosion went up significantly. And that seems to have happened across the globe, even in places where glaciers are not necessarily that significant. Maybe other changes to the climate have also affected things. So yeah, that brings us here. Just to quickly summarize, and if I was just to ask you, what are some of the different ways we can calculate exhumation rates? What do you think? We've seen a few. Surely we can come up with one. So, Yorina, what do you think?
The height and the age
Yeah, right. So this age-elevation relationship, we can use that. What else could we do if we don't want to do age-elevation relationship for one reason or another? What are some alternatives? Well, if you want. So what's the simplest alternative to doing that age elevation trick? Yeah, right. Assume some kind of linear constant gradient and calculate exhumation rates that way. Or you can go and use thermal models and things like that. Some of their advantages and drawbacks, well, I think probably the biggest disadvantage for this age elevation relationship idea is that you can't assume the isotherms are horizontal. And you often can't sample in a perfectly vertical fashion, so it just doesn't work for low temperature thermochronometers. And unfortunately, I think that's been kind of, people have been saying that for at least 10 years now, and still there are some people in the thermochronology community who continue to use age elevation relationships as a meaningful way to get exhumation rates. And I would advise you not to do that, should you be faced with that choice yourself. All right, so then the last thing here, can thermochronology be used to study geological processes across the globe? Yes, of course it can. We just saw an example. There are some complications when you go to places like where we are here, because the ages get older, and sometimes older ages don't quite behave the same way as younger ages. And the systems can start to act a bit differently for very old samples. But of course we can use thermochronology essentially everywhere that we can find datable minerals. It's just a matter of then how do you interpret the data, and that's, to me, that's where the really interesting part of the science is.